sometimes you have to try rewriting the problem in order to be able to do it. In this problem we have sine 2x and then we have e to the sine squared x. And right off the bat I kind of see this mismatch between we have sine of plain x but then we have 2x inside this other trig function. So what I want to try to do is maybe simplify that. Remember, the sine of 2x is the same thing as the sine of x plus x, and we have this formula for the sine of a sum. You take the sine of the first times the cosine of the second plus the cosine of the first times the sine of the second. And in this case, because both angles were the same, we have just 2 sine x cosine x. And that's actually going to help me do this problem. If I rewrite this using that trig identity, now I can see what to do, because if I set u to be the sine squared of x, then the differential du, let's see, we have sine raised to a power, so the power comes down. We get sine x to 1 power less, which would just be sine x to the 1, times the derivative of what's inside. The derivative of sine is the cosine. And so the differential would be du equals 2 sine x cosine x dx. Now in this problem you can multiply in any order, so if I rearrange this and move the e to the sine squared x up front, I really have e to the u, and then 2 sine x cosine x times dx is du. Now that I applied that identity and made this substitution, the problem is easy, right? The antiderivative of e to the u is just e to the u plus c. Substitute back, we chose u to be sine squared x, so we have e to the sine squared x plus c. This problem is pretty common. You need to find the antiderivative of sine squared of something, but it's really hard unless you remember this identity, that the sine squared of x is equal to 1 minus the cosine of 2x all over 2. Now, if you just remember your cosine identity, the cosine of 2x would be the cosine of x plus x, right? So if you know your angle sum identity, you know that you get the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second, which is cosine squared x minus sine squared x. But then because of the Pythagorean identity, cosine squared is 1 minus sine squared, so we have 1 minus sine squared minus another sine squared is minus 2 sine squared x. So that's actually where this identity comes from. If you solve this for sine squared, then that's how you get this. So if you're ever stuck with that, you can get that identity if you remember just your cosine of your sum identity for cosine. Okay, anyway, once we've got that identity, this problem is much easier. 1 minus cosine 2x over 2 would be 1 over 2 minus cosine 2x over 2. That's minus 1/2 cosine 2x. So I can rewrite the problem this way and just do two integrals. What has an antiderivative that is 1/2? Well, 1/2 x. What has an antiderivative that's negative 1/2 cosine 2x? I think it would be sine 2x. Let's check. If we take the derivative here, a 2 comes out. We want that to be a 1/2, so we're going to need a constant of 1/4 plus c. Okay, remember this one. You really need that identity, although you can get it from the cosine. So when you see that sine square, just think, oh, isn't there some identity that will reduce the power? It's actually called the power reducing identity. That's how we get that kind done. One more that takes a little fiddling I wanted to show you here. We have underneath this root x squared plus 1. Now if that was just a plain variable under a root, then I could just write it to the 1/2 power, and integrating powers isn't too bad. So I'm just going to try a substitution here where I set u to be x squared plus 1. Then du is 2x dx. Now actually I can conjure up an x dx in this problem if I borrow one of these three x's, and you can multiply in any order, so I'm going to move that x back here. So I have x times x up front still, and then I have x squared plus 1, and then this other x is back here multiplying dx. I can do that because I can multiply in any order. Now I know that x dx from the differential here, if you took 1/2 of both sides, you'd find that 1/2 du was equal to x dx. So rewrite this problem, and we have the square root of u, and x dx is 1/2 du. You've got to work on this x squared, but notice I can actually find a relationship between u and x squared, because if I solve this, x squared is u minus 1. So I actually have u minus 1 times root u. Now this is actually much easier, because we have u minus 1 times u to the 1/2. We've got this constant 1/2, which I'm going to bring out front, du. So we really have 1/2 times the antiderivative of u to the 1 times u to the 1/2 would be u to the 1/2, or u to the 3/2. And u to the 1/2 times negative 1 would be minus u to the 1/2 du. Now each of these is a power, so we could split that up into two integrals. We have 1/2 the antiderivative of u to the 3/2 du, minus 1/2 the antiderivative of u to the 1/2 du. And the antiderivative of u to the 3/2, that's just a constant power, so the power is going to increase by 1. And I'll need 1 over 5/2. Well, 1 over 5/2 is the reciprocal of 5/2, that's 2/5. And then I still have this 1/2 out in front. And back here, if you find the antiderivative of u to the 1/2, the power is going to increase by 1. 1/2 plus 1 is 3/2. Which I'll need a 1 over n plus 1 out front. 1 over 3/2 is 2/3. And then I also have this half here. Okay. Now just a little more simplifying, half of 2/5 is just 1/5, so 1/5 u to the 5/2 minus 1/3 u to the 3/2 plus c, and u was x squared plus 1, so I can substitute back. I have x squared plus 1 to the 5/2 minus 1/3 x squared plus 1 to the 3/2 plus c. Okay. Just another example where a little playing around with the problem can lead to getting the problem solved.